Okay, input output devices and motor controls. Identify electrical symbols for various switches. Describe the operation of proximity, Hall effect, ultrasonic, and radar sensors. These are ultrasonic systems. Name the common indicators used in PLC systems. Explain the purpose of using indicators in a PLC. Explain the difference between power relays. We'll look at contactors, magnetic motor starters, and control relays. Describe the operation of a relay. Describe the operation of a oscilloscope. Name the two major types of motor control devices. Name the two types of overload relays, and explain the difference between temperature and thermal overload. Push buttons are also called discrete Boolean. Some of the PLCs, especially I think the TIA Portal calls these Boolean. Boolean is kind of like Boolean algebra. So we have what we call a thing called Boolean algebra, which basically deals with algebra that we deal with symbols and stuff like that. Independent devices that connects to a PLC input or output that either allow or disallow electric current to flow through them. Can be physically changed to an on or off position, remain in that condition until its state is changed. So these are discrete devices. Discrete is what the book calls it. TIA Portal calls it bool. We'll call them digital or binary. All of those are exactly the same, mean the same thing. So these guys are either off or on. Push buttons and switches, we have what we refer to as a normally open. So we have a normally open switch, a normally closed switch, a normally open push button, and there is no such thing as a normally open push button held closed. But what would that mean? Somebody would have to be standing there the whole time. So I don't know what this guy came up with. Probably because we do have one that we have this situation with, and we'll even demonstrate that on the line back here, where that would come into play. But there's no such thing as a normally hold push button that's held closed. So just ignore that in your text. And normally I try to separate this more, so that should not actually have. There should be a slot in there indicating that is not there. Now these are what we call momentary contact. I need to come back and add that situation, that indication. So what we mean by momentary contact is when you press it, it makes the circuit, and as soon as you release it, it's gone. It's open. Normally closed contact, always closed until until they are forced open. And these are push buttons. These are switches. We'll look at how these things are nomenclature. And this is a normally closed push button, momentary contact push button. There's no such thing as a normally closed push button that's held closed. So this is in the book. A manual switch requires an operator to change their state. Automatic switches are controlled by a mechanical or electrical device. They do not have to turn on automatic switches on or off manually. Limit switches is one example, but we have all kinds of stuff. So these are some symbols, and they should be on one of your charts that I gave you. I've never seen this symbol right here used for a single pole double throw switch. So basically, what we're dealing with is on switches, and even relays. We have what we call poles, and then we have what we call throws. A pole is the number of switches that are controlled by the same operator. That means when I change the state of that operator, all the switches, all the poles change. That makes sense? The throws are the number of positions that switch can be put in that actually controls a circuit, a current flow or signal flow. So this guy right here is a single pole, single throw. So it's only got one switch controlled by an operator, and it only controls the flow in one circuit. But if I come up and do this and draw that, now of course now we got one switch, so this would be one pole, but it can be put in two positions that controls the flow, right? You understand, a signal or a current. So this would be called a single pole double throw. Now if I come over here and do this, and that below that, I'm going to do another one, and I'm going to put a dashed line. It means these are mechanically connected together. That means the same operator is going to control both those switches. So this is going to be a double throw, but on each switch only controls one circuit, so it'd be a double pole single throw. Everybody follow me so far? Then I could come up and do this. This is about as far as we go with these. We'll put a dashed line through there. So we have two switches controlled by an operator, so that's a double pole, and each one of them can be put in to control the flow in two different circuits. So this would be a double pole, double throw. Now above that, we usually go to something called a selector switch, where we can actually control a lot more contacts. But these are about as far as we can go. Now these are the same thing in push button. Okay, double pole. Okay, control one circuit, second throw. Double pole, double throw. Are we okay? Like I said, I've never seen that circuit. I've never seen drawn like this in why. So over here, when we draw circuits, we draw from left to right, and our lines are always horizontal. We don't have vertical lines. So on these symbols, are you okay? Momentary contact push buttons, also called spring-loaded push buttons. I've never heard it called that, but I'm sure it's right here. Lock position push buttons. Some people call it a vacuum push button. Some people call it a detented push button because literally they put a detent in the operator that it falls into. So you hear all these terms. So if I go back and hit that stop button back there, it does not pop out automatically. I have to pull it back. So what it'll do, a detent or lock position will stay that. You manually have to move it out of it. A momentary contact, you push it, and it does what? So these light switches, what would those be? Lock position, because you turn them on, and they stay on until you manually do what? Turn them off. Push buttons and electric switches, so these are just pictures of them. They have poles, throws. I should have brought that down. We got push buttons that we can do that we can add different contact blocks to them, where we can add more poles and more throws. And usually in industry, these are going to be big, so they can be easily seen. And another thing is so we can operate them easily with gloves on. That's one of the big reasons these. And a lot of your push buttons will have these shells around them. So you can't do what? Accidentally bump them. Unfortunately, our e-stop button, the way they've got it mounted on the outro line, we get that all the time. I get it all the time. Because I got to lean against something if y'all didn't know. Poles, the number of switches, are push button controlled by one operator connected to a movable contact. Number of places in which a switch opens or breaks circuits. Throws, number of switch positions that controls the flow of current or signal inside ours, we are going to control the flow of the signal inside of our. Now we do have in industry, we have what we call double break and single break, and I don't know if they show that, but on a single break, what we would do is we would come over here, and it would technically look like this, even when it's wired. On a double break, what we would have was we'd have a contact on this side, a contact on that side, and then the operator actually comes over and does this. And this right here will be on a spring. So if it's momentary contact, it'd be on the spring. And what advantage does double break have over single break? So you'll run into a lot of push buttons out there. One. And a lot of relays, we have double break contacts. So when I look at this relay right here, these use double break contacts. I don't know what's going on with Ethan. Came in real late. So what advantage those double break contacts, what do they have over single break? Huh? Well, the problem we have, number one, is we have two chances to break a circuit in control. And plus these things, every once in a while, we have a problem with these contacts that control the relay. What happens when we're controlling a lot of current, and every time we set the break, we have a little R. Every time we make a R. That's way up. What happens every once in a while is we have a contact control. So what happens I need to draw this because it's recording. If one side's welded together and it breaks, it literally does what? It tilts up and has a tendency to break the weld. So these guys have two chances to break a circuit. Single break contact only has one chance to break the circuit. A double break contact has two chances to break the circuit. And plus, a double break, you can actually see on that one, if you touch it, you can actually move your finger. So if one side gets welded together, it'll tilt up and have. So when you got something that you're trying to break loose, you usually tilt it up, right? You understand? So it has a better chance of not welding, breaking away. So yeah, just about all, not all. Those are the contacts. The push button, double break contact. Industrial switches are designed to work in harsh environments. Industrial switches may be exposed to extreme humidity, flashes, liquids, gas, liquid vibration, and high electrical noise. So that means these guys are usually sealed up real good. So you can probably operate some of these things underwater. So here are some manually operated switches. This is what we call a distributor. Still manually operated. Then, of course, snap switches, the wall switches, electric switches, guys are. You don't see very many regional things like this. Guys are really hard to operate. The first actually temperature sensor. So, what is a sensor? What is your sensor do? So what is your sense? Well, your brain cannot see. Your brain cannot feel. Your brain cannot hear. So it depends on sensors. So what does our sensors do? What does our brain process? Your brain processes two things: electrical and chemical. Chemical is like when you're scared, right? You understand? That's a chemical. Right? But when you touch something, I come over and touch something, my nerves takes that physical stimulus, converts it over to electrical signal. This travels up, goes to a certain section of my brain, and it comprehends, and my brain processes electrical signals. Usually analog, right? You understand that? So what do our sensors do on these manufacturing lines? What do they do? So my sensors take electrical stimulus, converts it over to electrical signal, so my brain can process. So what do these sensors do? They take physical stimulus, converts it over to electrical signal, so we can process it. So they do exactly the same thing that your sensors do. So we have temperature sensors. So these guys are going to somehow sense temperature, convert it over to electrical signal that I'm going to bring into and here we're going to bring it into a PLC, and the PLC is going to process. So we have digital temperature sensors, and then we have analog temperature sensors. We just book doesn't even get into. So the problem is when the book was probably written, there just wasn't that many people that had analog capabilities on your PLC. Now, of course, just about all PLCs have analog capabilities because of these guys like these. Detects a specific temperature preset, so they're talking about digital. So when you take sensors, the one that we use, we have two presets, so we have an upper and lower. So what happens is, normally these sensors, especially electronic sensors, have what we call a deadband or a span. Because if it didn't, it would constantly. So if you ever watch the temperature on your air conditioner, as soon as it drops down, so you get up to 70 degrees, if it drops down to 70 point something, it don't turn back on. It's got a span, right? It's got to drop down probably 1 degree before it turns back on. Because what would happen if your system was looking for exactly 70 degrees, what would happen all the time? It'd be cycling. Because as soon as it turned off, the temperature would drop down a little, it'd turn back on. So all these sensors, all these digital sensors usually have a span. On our temperature sensor, you can actually set it. Using vapor pressure technology to sense the temperature, that's not exactly. We do have some that actually depends on expansion and contraction of air due to heat. I was working on a automatic boxing. It was Gerald's Milk, where they actually did powdered milk. I don't know, does Gerald still sell powdered milk in the grocery store? I don't know. We don't buy it. But the place that does it was right here in Bessemer. And the thing that automatically came from a hopper, poured into a sack, sealed the sack up, came down, counted out the number of bags, slid them into a box, went down, automatically folded the box over, applied glue, folded the box over, and that glue had to be at a certain temperature. But what they used in the temperature was just a bulb, and it had air in it. And what would happen when the glue would heat up, the air would expand and it would go over there and trip up a pressure switch. So it was a temperature switch, which was really, really cool. So that's undoubtedly what this guy's talking about. We have all different types of ways we can sense temperature. So when he says uses vapor pressure technology to sense change in temperature, that must have been it. We have temperature, we have thermistors. This is usually what we use in our house. And then we have thermocouples. That's only two I can think of, besides for pressure. Offers many features and modifications allow them to be used in a variety of applications. But what does a temperature switch do? It senses what? Temperature. Where do you have one of these on your car? So you have a light. Hopefully you got a light to come on when your car starts running hot. So that would be a temperature sensor. You got one of those in your radiator. So these are just the different variations of temperature sensors. These are, this is double fold. That should be on those handouts that I get. So guys, when we take breaks, they're 10-minute breaks. So I'm gonna start lecturing. I got an alarm I put on my watch, and when it gets 10 minutes, I'm gonna start lecturing. If you're not in here, that's just. Are we okay? Yes, no. Pressure switches used to detect low and high pressures in a pollution system. So assemble or pressure switches. So what we're talking, why do we need to learn these? This is PLC. Why do we need to learn? Yeah, because I come over here and I have my PLC and I have input 0. Well, input 0 is going to be hooked up to something. So that means if I come over here and I have a pressure switch, then over here, you've got to use these symbols over here. So on the side where you wire them up, then we use the symbols. So I'd come over here and I did that, and that means that is a pressure switch hooked up to that input. Now in my PLC program, I'll come over here and do that, right? You understand? Or vice versa, depending on what we're looking for. So if you don't know these symbols, then you couldn't draw how you wire them up, or you couldn't wire up a PLC because you wouldn't know what symbols they represented, right? You understand? So this is why in program controllers, not only you got to learn the symbols of programming language, you also got to learn the symbols of the devices that we connect to the PLC. So these are examples of pressure switches. I got one of these. I don't know if I've got it. So this is like the one that they go. This actually came out from that like but we have both modes going on inside the heating, ventilation, and air conditioning system. And this is an audio thermostat. This guy used a little thing called a thermistor, which sets the temperature. So this was definitely analog. So this little low thing with a white dot on it that's got the holes under it. This is the temperature sensor that this thermostat used to sense the temperature of my house. Of course, this would be analog. So like I said, the book basically was written when most of the things that were hooked up to the PLC was a analog sensor. Digital sensor. But now we have the ability to handle analog. And what we have to do though is we have to take an analog signal and convert it into a binary. We got what we call an analog to digital converter. This is what's in your multimeter. So that multimeter is not, that display is so you measure an analog signal, but it displays digital information up on your screen, right? So most of your PLCs have these, even ours. So if you look at your PLC on the top right-hand corner, and it can be from 0 up to 10 volts. Most of our signals go from 0 to 10 volts. And we'll take that and convert it into a binary number. So ours have what we call a 10-bit A to D converter. So how many combinations can I get out of 10 bits? 2 to the 10, gives me 1024. That means it's going to take that and convert it into a binary number between 0 and 1000. It's going to be binary. We're not going to go through that. It's going to be a 10-bit number. I think the Siemens has a 12-bit analog to digital converter on it. That means it can take it and split it into 4096 combinations. So it would have better resolution. And then we'd have to learn how we would use that number in our program. So basically this deals with nothing but digital type sensors, which is what the pressure sensor that I gave actually came off of a compressor. And you look at it, it's got low, it's got off and on. It turns off at 100 psi and turns on at 70. If you probably notice, all the hand tools you buy for your compressor are supposed to operate at 60 psi. A liquid level. Where do we have a liquid level sensor at in our cars? On gas, yeah. It's the one that comes on that says you need to add fuel. So we have an analog sensor that tells us the amount, but sooner or later, if we let it get down, it pops up and says, so that would be a digital sensor like this, and it's technically nothing but a flow like this. Huh? Yes, it's a flow switch. Yeah. In fact, it's the same thing. It's the same switch. So if you ever pulled up the sensor on that, you see a little float over there. And then it basically uses a potentiometer that comes up and moves the float switch, and that's where it gives you your analog. And then when it gets down to a certain level, it trips your need fuel or whatever you're saying. I had a Honda Shadow, one of my motorcycles, and it had that line. My Harley, though, it just went dead. But it had a dual, if you ever took the gas tank apart, it had 2 levels on it. Up here, and then when it dropped down below that, it had what they call a reserve. And then what you had to do is while your bike would start stuttering, you lean over, you got used to it and turn it over to reserve. Then, if you forget to turn it back to normal, you run out of gas. I run out of gas once. Because once I filled it up, I forgot to put it back on the other setting, and I ran out of gas and I reached down there. So I didn't like that. I liked the Honda with the light. Well, the Honda was shaft drive and radiator cooled too. But the Harley was thin. Float switches. If I was going to go on a long trip, I rode the shaft. Float switches used to open and close contacts, responds to change in liquid levels used in water treatment plants, wastewater treatment plants. You got a float switch in your commode. Instead of controlling the flow of electricity, it controls the flow of water, but it's exactly the same. Exactly the same. So this is a symbol for a float switch. It's kind of like a pressure switch. It's a full circle, normally open, normally closed. So notice you're normally open, on the bottom, normally closed, what you're at. This will be not more than so these are different flow switches. Now this is the kind of like the one, so these would be the ones that actually flow. These are the ones that are actually electronic. So what happens is you pull up, change but all the rest of them we'd have two tubes that would go down. We'd have an outside tube and an inside tube. And they were capacitors. And what would happen is the fuel came up between the two to change the capacity. And that's the way ours. I don't know what other airplanes were. Most times we had about 3 across the top of the wings, and then we had 3 on the bottom of the wings. And they were all averaged together, so no matter what altitude the plane was in, it gave them the right fuel. So we had what we call a wet wing tank. My planes I worked on had wet wings. I can't remember. I think like 2,000 gallons they could put in each wing. And then it had a belly tank that was 5,000 gallons. So it could hold around 9,000 gallons of gas, or JP fuel, jet fuel, which is kind of like kerosene, by the way. It's a little different. And that was one of the systems that we had to work on, by the way, fuel system. Going back. Flow switches. So flow switches detect flow of a fluid. A fluid is a gas or a liquid, right? A lot of people think, so how do we define a fluid? Anybody know? Anything that has no fixed shape, it takes the shape of whatever it's in, and it moves freely. It gets with a difference of potential. So that would be a gas or a liquid. So gas we call pneumatic, and fluid we call hydraulics. A foot switch uses emergency or contact switch placed in effect on a factory environment in which workers are used both hands. I've seen these used a lot on presses. A lot of, sewing machines use a lot of these. People do a lot of sewing where they got to handle the fabric with hands and usually turn the sewing machine off and on with foot switch. I've seen them used a lot in presses where the guys have to put the piece of metal in there, get their hands out, and press the wheel. These are just foot switches. Usually they got a guard around them. The ones sewing machines don't have. I like that. Yeah, you can't accidentally step on it. You got to actually step it in there. So this is a symbol for a normally open system. That should be on the symbol chart too. Limit switch is physically touches eye part, opens and closes when an object physically hits the actuator. Consists of an actuator that is mechanically linked to a set of contacts used in a variety of applications for protecting the presence of parts. These guys right here started automation. Or when we could sense when something was in a certain limit or hit something, we could cause things to reverse and change. So limit switches. So we're going to have the operator that will normally close. Here's where we get into these held open and held closed. Because what we're going to do is these limit switches are going to be in a certain position, and we're talking about when the machine is in its normal position. So if we go back and look at gravity's trying to close this one, so it must be what? Held open. Okay, see how you do that? Here, gravity's trying to open it, so it's normally open. Here's gravity's trying to open it, so it must be held closed. So you look and see what I'm talking about?
Like this, like if I had water and things and the operator uses water in the tank, I would have to switch that to water in the tank. You know what I'm saying? And depending on what I needed, I have no idea.
Yeah, and what you need in your program depends on what you need for the program to do. That decides which one of these symbols right here you use for the switch. So I'm saying we could use it multiple times. So this is what's so great about a PLC. Normally, if we need multiple contacts on these things, they usually give us one contact. Sometimes they give us two. Sometimes it's a single pole, double pole, double throw, but one of them will be a normally closed throw. But over here, I can have a single pole, I can have a single pole, throw. And I can have a single pole, I kind of have a contact. Contact. Yes, that's what we normally use. It all depends on what you want to have. So if I want the light to come on, when the thing opens, all what's there, the only time we're really concerned is when I see the guy right here. This thing will stop. There's no doubt that I'm it's only one, if we're only using one contact, of course, it's but what I want to do, I'll something open, or I'll you as a programmer decide which one of those symbols you'll use. That's a really good question. And these are, of course, these are heavy duty right here. And these heavy duty, you can get different types of operators. Some of them you can actually turn the head out of them. This guy right here, I can actually change out rotary. These can make whip type, punch type, angle type, double strike type, or type. You don't see much of this on those little pilot ones, but they're not picking up that one. But these are contacts. So these guys have to make physical contact with what they're trying to see. And these are basically the only what we call physical contacts. Float sensors might be considered physical contact because they actually have to get into the liquid. Temperature sensors may have to touch something to see if it's hot. It might have to make contact. Others might be non-contact sensors. What's an RTD? Temperature device. So what determines the resistance of a wire? The material, the size, and 3 is the length, and then 4 is this guy right here. And it is very accurate. So if you know the expansion of this ratio, I took a physics class. We actually measured how much the resistance of a metal changed with the rise of temperature. So that was that one thing that we passed around. This guy right here is an RTD. Thermocouples are made out, it depends on the temperature range that you want, but they're just similar metals. And they set up what we call electrolysis, which means they literally create a voltage that's proportional to the temperature. And they're very accurate also. That you use two different metals depending on the temperature range that you want to make. So you got a thermocouple in your oven, they're real accurate, and you've got a thermocouple on probably if you've got an electric water heater, or even a gas water heater, you got a thermocouple, and that's what it.
I thought you were talking about the oven in my job. You're talking about the oven in your house.
Yeah. So this is an RDT right here. So all it is just a bunch of, now normally in industry it'll be encapsulated inside of either a metal tube or a ceramic tube. But all it is just a bunch of wire, this fine gauge wire that's wrapped around some ceramic rod, and they just put a voltage across and it changes the current. Its resistance goes up at temperature. And they're very, very rugged. They're not a liquid. These suckers will last forever. Thermocouples, you have to run the exact wire, whatever the thermocouple is, that's the wiring you have to run all the way to the gauge. So we had our engines, our jet engines had about, good gracious, they had a loop around the combustion chamber thermocouple. They monitored that combustion really, really well in that jet engine. And we had a wire that broke off one of our thermocouples. And we went out there, we didn't know this, even though we were electronic. And we got a regular old splice terminal, stripped it off and put a splice terminal on there, spliced it back off. And that didn't work. Yeah, it changed everything. And we couldn't fix it. So, luckily our plane had four jet engines on it. So they had to fly that plane back to Lockheed to get that thermocouple, that section of that thermocouple loop fixed. So, but we didn't know it. We just crimped a regular old terminal on there. And when they fired that engine up, it was interesting. They got kind of choked up when they saw that temperature reading on that turbine inlet temperature is what it was called. It was it's coming out of the combustion chamber. It went into the turbine to determine how fast it was. Yeah, they're pretty. Look at that pretty much. Of course, these are electronic duty limit switches. Like I said, PLCs are fine. But PLCs, they're running electronic load, so the current requirements out of them almost nothing. But if you're going to run a load, then you're probably going to use one of these heavy duty ones. And they're still all over the place. They're cheap. They're very reliable. The biggest problem we have is their electromechanical devices, which means what? There's two ways they can fail. And the biggest problem we have is people going out there making adjustments on them or checking them with a measure, and sometimes they don't back on them. Or coming out from the bottom, it's got a little bit of wiring still on it, and they won't back up. They're pretty. Electronic sensors used in PLC control systems to detect the change in the environment and industrial settings can emulate the 5 human senses and convert. Actually, we got a lot of senses. But these are the main ones that take physical stimulus and convert them into an electrical signal that we can process. Emulates the 5 human senses and convert the change to electronic systems. With non-contact, technically a limit switch is a proximity. So proximity means we're looking for something when it's at a certain spot. The limit switches, like I said, these were the first ones that came out. They got that name because technically that's the first used to detect limits. You can see them like that. The limit switches technically are proximity sensors, but we don't use that in the field. It's just like disk operating system. So when the first disk operating system came out, and this was an operating system that you loaded into your computer off a disk, and we call that DOS. Well, the problem is, for years, so Windows XP, Windows 95, these are all DIS operating systems, but they didn't want to call them DOS because that name had already been used by the first text-based one. So they start calling them Windows and then Windows XP and Windows 95. What version of Windows are we on now? Windows 11? So the term proximity means these are non-contact systems. Can be detect the presence of an object. Electronic signals used to detect an object. So object does not have to be touched. Can only have a state that is either true or false. Can either be inductive, capacitive, or optical type. So we have all of these here. We'll look at. This is very, very important. So we can set up our PLC different ways, especially this one. Some of them are fixed the way we do it. Our PLC, we can set this up. So we come over here and we have the input device itself. And then we have the input to the PLC. And then this over here has to have a pump. So I got two things I can do. So this is connected. So I come over here, and if I make this plus, and I connect my input to that, then what does this have to connect to over here? To get current flow. It's going to have to connect to a minus, right? You understand that? But if I come over and make this a minus, then this over here has to be a what? Plus. So what they do is it all depends. Some PLCs allow you to set the common. So on our PLC, we can set the common. So if you look at the very top, I've got two common. That's what it's called common. I can hook up the plus up there, or I can hook up the minus up there. Everybody understand that? So what we have is we have the ability to do this. So NPN, and these are the names of the sensors, and this all came from digital, by the way. Syncing and sources came from digital. So syncing, then syncing uses a negative sign. So this would be negative. And this sensor right here would have to be, if it's a solid state sensor, it would have to be an NPN sensor. And then this right here over here would have to be positive. You understand that? So if I connected negatives up here, then my PLC would have to use a positive column. But if I bought the sensor, I would have to make sure I had an NPN sensor. So an NPN sensor is a syncing sensor. A syncing sensor means it's going to be powered by the negative. Now these are DC sensors. If we got AC inputs, it makes no difference. If we got DC, or if we got a push button, push buttons don't care. Electronics care where you put your negative and your positive. If you don't believe that, go out there and swap the battery cables on your car. You won't be able to do that. You might be able to can get some extensions. Other, you're going to burn up a lot of stuff, right? A whole bunch of fuses. So electronics are sensitive to the polarity that you apply to it. Now, if I come over here and this is a plus, if this is a plus, that means this is a plus common. So this over here has to be a minus. And now I have to use a PNP sensor. This has nothing to do with push buttons. Push buttons don't care what's negative and what's positive. Switches don't care what's negative or positive. Electronic sensors do care how you use them. This is the way our PLC is hooked up. It's hooked up as sourcing. We got sourcing input. We got syncing inputs. So our sensors use a sourcing PNP sensor. Are we okay? That makes sense? And why? Well, companies make, you need an optical sensor. And this company makes both the PNT and the NTN, but you get the wrong one. You go, okay, I need a through the beam sensor. You go up there and say, oh, there's one up there, right? And you buy the wrong one and you hook it up, what's going to happen? It's not going to hurt the sensor. The sensor just not going to work. Oh, they sent me a bad sensor. Let's order another one. You order the same one, put it in there, it don't work. Oh, the PLC's bad. Let's replace the PLC. Put it back in there, it don't work. Right? You understand? Because you're buying the wrong sensor. This becomes very, very important, guys. So you need to know what your PLCs are running. If it's running syncing input, you got about sourcing sensors. If it's running sourcing input, you got about syncing sensors because you got to have optical polarity. Y'all understand that? Yes or no? This is most used. All our PLCs in here are syncing input, sourcing sensors. And by the way, the EduTrainer does that. President's motor control, ladder diagrams, all proximity sensors use the same thing. What we do is we take a simple number of units, put a diamond shape around it, and if it's a high voltage sensor, it might be a 2-wire sensor, which means it powers up to the low, so the sensor fails. So we got 100 of those. It drops about 4 volts, but that's still leaving 160 volts around the low. But if I'm running a low load sensor, like if I'm running on a 24 volt supply, then odds are we're going to have to power that sensor up. So this is what we call it. For some reason, don't ask me why, Germans use brown for plus. It uses blue for minus, and black is the signal. So if it's a 2-wire sensor, this wire right here will be blue, because it's 24 volts. And sometimes they'll number. This will be 1, 2. No, that's right here. Power is even. 1, 2. About 3. 4. I'll throw this head up. No, the big colors we use, but if it's a 4-wire sensor, which means it acts like a single pole double throw, then this will be white. Now normally these solid state sensors give you one contact, or it gives you a normally open and a normally closed contact. If I need more contacts in relay logic, I'll have to add a relay out there. In PLCs, it makes no difference, because we bring in that one input and we can assign it to 100 software contacts if we need. So we can go back at the line and see these. A proximity switch, non-contact, light emitting diodes. Let's go ahead and take another 10-minute break, guys.